So the goal today is to review how to do, to go over how to do R, particularly the test statistics. We will do the Z test because the Z test cannot be computed directly. And then we will do a T test, okay? Also cannot be do directly. And then for T test, you have the thing already, okay? So then we will do the two-tail test, okay? And then the F test. Okay, so that will be the goal. So I hope you open the R Studio with you, okay? And then after R Studio, we're going to start, okay? So the script is here, okay? So here I have I try to first make the font size bigger first, because this is at 14, because usually that is too small. Okay, so now I can get started. Okay, look at the slide we have for the Z test. Okay, so the Z test here is actually we have to construct from the scratch. Okay, the reason why is because they don't have a Z test. Okay, so we can write a function for it, of course. Okay, and we have to start from scratch to calculate the mean. Okay, and we're going to give the hypothesis testing. Okay, so that is, let us construct from the scratch, and just to remind you how the formula, right? Just write down the formula here, and then we construct from scratch. Okay, so basically the T test, the Z test is like this, right? It's like the following, all right? This is the test statistics, right? So we'll do this, and we'll do a p-value, and that's the goal. Okay, so we start with the data. Okay, the data we call X, right? So let's get started with the data first. Okay, the data we have may be just C of any number you like. It doesn't really matter. We just input some number here. Doesn't really matter how many we have. Okay, because R is just a very convenient way. You can, no matter what you put, it just computationally very fast. Okay, so this is the data we have. Okay, so we can actually calculate very quickly the X bar, right? X bar, which is the mean of X. Okay, so first we input it. This is data here, run it first. So after you run it, you can see the data is in the value in the environment, right? It's there. And second thing is we calculate the X bar. Okay, X bar is the mean. Okay, it's here. Okay, here is, I don't know, for this particular case is 3.5555556. Okay, it doesn't really have to be this. It just I just print them randoms. Now, the next thing is we need to know the mu, right? Mu is, I don't know what you want to input in. Okay, we can just put somewhere at the beginning, right? Because it's given, right? Mu is like, I don't know, we want to test which is 4, right? And sigma, okay, is also, the thing is given, right? You do a Z test, sigma is also given, maybe just 0.5, I don't know, just something we think that is reasonable. Okay, and then we have coded n, right? N is length of X. Okay, so that would be everything is there, right? So basically you can do this by the Z, which is X bar minus mu over sigma over root n. Okay, so that is a z. Okay, once I have a z, then we're done, right? Because of z, we know what kind of hypothesis we want to do, then we are done. Okay, so suppose we want to do the right tail test, right? Suppose we want to right tail test. Okay, right tail test is suppose maybe I want to do the p-value of the left tail first. Okay, p-value of the left tail. Okay, we want to do the p-value of the tail, so we want to do p dot left. Okay, left tail. Okay, and what is p dot left? It's just the d norm, right? Okay, of z. Okay, because norm we don't put anything, it's just standard normal. So there's a distribution of norm. So we're done. Then this is the p-value of the this is a set test. That's it. So you see our I haven't done some problem or x bar to be small. Yes, so that should be fine. Okay, so I want to get the number out. Okay, let's get the number out. What's the p left? Okay, so I have the p-value, which is 1%, right? So the thing is here is I would reject the null at 5% or 10%. Okay, so I let you to do the right tail test. Tell you do the calculation for the right tail and the two tail. Okay, that's exercise for you. So I give you to do the right tail and I do the left tail for you. You do the right tail. Okay. So I give you a. So this is the left tail. Okay. This is left tail p-value. Okay. So what I want is to do two things. I want to do the right tail p-value, and I also want to do the both tails p-value. Okay. So this is so test of this. Maybe I put the hypothesis here. That would be a more elegant. Okay. So just reschedule everything. Line 1 to 3 is the data, and we do the z-test statistics. Okay. So I want you to do the other tail. Try to work it out. What is the right tail, and also what is the both tails? Okay. Or two tails. I mean, try to work it out a little bit, but if you understand the relationship between the left tail and right tail, it should be fast. So let me show you the right tail, okay? Because the left and right tail just do one way or the other, right? So just D norm Z. You can just show the answer. Okay. So the right tail, as expect, right, is 1 minus the left tail. Okay, so when the left tail is actually 1%, the right tail is actually 98, right? Because they're complement of each other. Okay, the p-value of the left and the right tail should add up to 1, right? So that's why it's 1 minus, right? This is area to the left of the Z. Okay, so now the next thing is to both tail. Okay, so there are two ways to do the both tail. Okay, but I left you to try a little bit. Get it right. So how to get a two tail? There are two ways to do it. Okay, two tail. Okay, one is to look at, because I want the minimum and then multiply by 2, right? So I can do the following: 2 times the minimum of the left and the right. Okay, so that also gives you the answer. Okay, and this is what I do in the class in the slide. But also, if you remember, the slide I write in how to calculate two-tail p-value, right? Can be also by doing this. Norm of absolute value of the set. Okay, both give you the same value. So this one gives you around 2%. Or maybe I have to do, there's only one way. Okay, so this is the way, and either you do the minimum of this number. Okay, so that is the two-tail. Okay, so now this is a z-test. Okay, I think you can do the t-test. Okay, let's do it. Okay, do the t-test by yourself. Let's do the t-test. Okay, so give you 3 minutes. Okay, just you can change several areas, then you can do a t-test. Okay, so for the d norm, you change the t with the dt. Okay, and then you have to tell them the degree of freedom, and that's it. Okay, so basically what you'll be doing will be, instead of doing this, you have this. Okay, you have the t statistics. Okay, and then of course this will be dt of something. Okay, dt of something. Okay, and then you have to calculate t distribution is what? Okay, remember you have something here. Okay, and we no longer use this sigma, we have to do something, maybe SD. Okay, is certain thing. Okay, so basically if you do You fill in the question mark, then you're done. Okay. So just try to fill in what are the question mark. You change according to the t-test. Okay. So this is basically how you do t-test. Right. Just to remind you how you do the t-test. Right. The t-test, the math is like this, right? T is just x bar minus mu over s over root n. Okay. So basically you have to replace the sigma by s and remember what's s. Okay. I hope at this stage it shouldn't be difficult for you. Should be able to build it from scratch. Yeah, this is a t-test. Of course, it has to be t, right? Because this is t. It has to be t. T here. Okay. Okay, so let me show you this. Okay, the standard deviation is just SD of x. Okay, maybe S is better. Right? S here. This is n minus 1. This is n minus 1. Okay? And everything is done. Okay. So suppose you're given certain mu, right? And then this is the t-stat. Okay. And then this is the left tail test. Okay. Turn out to be left tail. Now you cannot really reject it, right? Because in the normal you can reject it. Okay. But when you have a t-test, you can't. Now because p-value is like 20%. Okay. And you know the right tail is already the complement, 41, 72. And the two tail is 50%. Okay. So this is how you can construct your t-test by yourself. Okay. And of course, as I saw in the notes, okay, you don't have to do that, right? Because of the fact that there's something called t-test, and we can say x alternative. Okay, we can just show you how to do it. Okay, the t-test actually you don't need to build up your thing, so you can alternatively, instead of doing this, you can do t dot test. Okay, x. Our alternative is equal to left. Okay, left dot tail less. Okay, and our mu is 4. Okay, and our confidence level is 0.95. Okay. Oh, sorry, the data is big X. Okay. So you can see this gave you the same value here, the T value. Okay. This guy, same as the T we construct. Okay. And P value will be same as the P left we should be same as the P value we construct. Okay. Okay. So you also want to do the right tail. Okay. The right tail will be just more. So the greater. Okay. So two tail. Okay. Okay. Then you can do the it's weird. So the two-sided is to do in this way. Okay. Okay. This is one sample t-test. Okay. I think there's some problem with the R when they calculate the t-test. Okay. But I will check out why they have some issue there. SD, right? Oh, sorry. Sorry, I think it's my mistake here. I should use P. Sorry. Now it should be all right. Yeah. So I'm sorry for the, I think I have made a mistake also in the, I also have mistake in the Z test. So instead of D, of using the P norm, sorry, it should be P norm. So, yes. So it should be P norm. I think the typo in the notes. Yes, the density function. Yeah. So just to remind you that there's typo here. I should use P norm or the D norm. Okay, because it's not there. So just make sure that you understand what I'm saying. This is the P. Okay. So this is the P norm. This is P norm here. Okay. So just to, that's why there's some difference between my answer to the answer. Okay. So just a reminder how we do it. Okay. So the Z test is the same, but I use the P norm. P is the inverse. Okay. So the same thing. And the T will be the PT there. Okay. And PTM minus 1. Okay. And when you do less, there's a give you the T test. Okay. And also give you the confidence interval. Okay. So that's very quick. Okay. Before we go to the two-sided test, any question? So that's how you do the all the P test. Okay. Maybe you want to try the okay. Let's do the proportion case. Okay. Since we do this, okay, we can do the proportion. Okay. Let's look at the proportion data, and we can do a. I don't think we have the put it there, but let's do proportion data by ourselves. Okay. Suppose the proportion data is like this. Okay. X is just bunch of 0 and 1, right? 1, 1, 1, 1, 0, 0, 0, 1, 0. Okay. So we need to do a Z test here. Okay. Do a Z test here. Okay. So first you need to calculate P, which is sample proportion. Okay. P will be just mean of X, right? Okay. Just mean of X. Okay. And then we do a Z test, right? We do a Z test here. Z test here, if you still remember the formula, will be just Z will be just, if you remember the formula, let's write down the formula here. The formula is P minus pi over pi 1 minus pi over n. Okay. So pi is our hypothesis. Okay. Pi, I don't know, 0.45, say. Okay. That will be P minus pi. Okay. And you take the square root of pi times 1 minus pi divided by n. Okay. N we haven't defined yet. N is the length of X. Okay. So now based on this, we can do a left tail only because the right tail is the same thing and they both are the same thing. So how to calculate the left tail, right? P dot left will be just the P norm of Z. Okay. So this is the left tail test for the left tail test for the proportion. Okay. If you want, you can try the right tail and the both tail. Okay. Try to see if you understand how the binary data. Okay. So that is how you do the Z test. It's not in the notes for this one. Because I think that would be easier. That's easy enough. So that's why I didn't put it there, because you should be able to do the proportional test, right? So this proportion is CO1 data. You calculate sample mean P and calculate how many data you have N. This is the set test. Okay. You should be able to do the calculation quickly. Okay. You can see it's much more convenient than Excel. Okay. I think much faster. Because Excel, you have to, when you change things, you have to compute again. But here, just very clear. What are the variable? What are the symbol? You can just input the symbol rather efficiently. Is there any question? So the P norm is just the norm dot S inverse in our Excel. Okay. Is there any question? If no, then let us do a two-tail test. Okay. We are not going to go to construct from the R from scratch. We just use the built-in function. Okay. Because you know how to do one tail, two tails should be the same. Okay. You should be able to do it. So what I need you to take it is look at two-tail test. With same just test, you just give two variables. Okay. So let's do the two-tail test. We'll do an equal variance, and we'll do an unequal variance. Okay, and I do the pair. Okay, so let's do one by one and do F test. Okay, so let's do one by one. Okay, let's do the let's get the data first. Okay, X the data. We have now we do an equal variance, so it means that we don't have to have the same number of data. Okay, so just randomly put some data there. You don't have to follow me. I just randomly put up some data. Okay, and this is Y, the data. I just also randomly put some data there. Okay, and to make it more fun, I just don't make it the same number. I just add some number there. Okay, so you just don't have to follow me. So we do a t-test, okay, under equal variance. Okay, and there will be t dot test. Okay, give the data X and Y, and if you forget the syntax, just do the t-test. Get a question mark and t-test. Okay, and here on the right hand side, question mark t-test here. Okay, and you can look at the syntax. Okay, X and Y, and we want the alternative equal to, I don't know, we want maybe a two-sided test. Okay, and then we wanted the variance equal, okay, is equal to true, because we want, and if you don't put in the 95%, it will be 95%. Okay, so this is optional. When you do 95, okay, but just put it there. Okay, so this, you run it, this is the t-test. Okay, I haven't do it right, so I have to run the whole thing. Okay, so this is the result we have. Okay, two sample t-test, X and Y, calculate t, and this is df is 22, 21, you just add up how many there. X have 10, Y have 13. So nx is 10 and 2 is 13. So add up 23 and minus 2, right? Because it's n1 plus n2 minus this. Okay. So if you don't like this, you can use x1, x2, because I think this is more. I think this is more in line with your handout. So let's do this again. So the same thing happened. Okay. So that's a two-sided. Okay. And the p-value is here. Okay. The p-value is here. So that means p-value is here. Okay. So that means that you would reject at 5%. Okay, in my case. And you also see the confidence interval. Okay. As we said, are all negative. Okay. So that's why you can reject it from 0. Remember the relationship between confidence interval and hypothesis testing, right? So you can also do the left greater than or less. Okay. So you can do the same thing. Okay. Instead, you do left. Okay. And then you can also the same thing and you do greater or do less and greater. This gives you the other result. So less will give you the almost the same answer, except you have the a different p-value, right? Because you only do the left side, right? And you also can do the greater will be the right tail. Okay. So much bigger, right? But you know that the p-value for the left tail and the right tail add up to 1. Okay, so that's it. So you know, right? And the two tail will be just 1 minus the minimum times 2, right? So that is the equal variance. Okay. So you can easily see the option here, equal variance. Okay. So try to do the same data by changing the variance equal, okay, to false. Okay. Then we have the other test that is unequal variance. Okay. So that means what we will be doing is just copy this everything there. Okay. From there, you have unequal variance. Okay. That means that this is false. Okay. Then this is, then you're done. Okay. So this, if you run this, and this unequal variance. Okay. So it will give you, depends on what you're looking. This is the watch t-test. But this is the case where they call watch t-test. So almost 1% is fine. Okay. Of course, this is very big, cannot, right? And two tail is also okay. Okay. So that is how you do the not equal variance. Okay. Unequal variance. It's okay. I hope just run over that. You're able to handle this. Okay. So now next I want to show is the paired. Okay. Pair is very simple, but we need to construct data. Make sure that they have same number first. Okay. So here are the different numbers. So make sure the same. Just take out the last thing. Okay. So the same number. Okay. Now we can run the pair. Okay. Paired. Okay. Paired means that we will say paired true. Okay. We just need to tell it is a paired data. Okay. Same data, we just do this pair. Okay. And you run this. Okay. this will give you a different p value for one left tail, okay, greater than, okay, also the not equal to two tail, okay, all the p values here, okay, and then you try. Of course, we can do it from scratch, okay? That's not difficult from scratch. Let me tell you how to, let's do it quickly from scratch here, right? Because you can define a function called d, okay, which is x1 minus x2, okay? And then you can also calculate s is also the sd of d, okay? And then the t statistics will be just d over square root of s over n, okay? We have to define n is the length of x1. Doesn't really matter which one you look at, okay? So you should be able to see this t should be this number, say, okay? Let's see whether you get it right. Th. Okay. So this t we get. Oh, we have to do the average thing. Haven't done. Okay, this the. We have to do the d bar. It's the mean of d. Okay. So the answer. Okay. So this t is 3.-3.4. So should be right. Yes. Okay. So this is data x1, x2. Okay. This is a length. This is different between the two items. And this is the mean, right? Because remember the thing is d hat minus 0, okay? And you have sd over root n. Oh, okay. So we have s over root n. Okay. So this is a t, okay. And this negative 2.18 is same as the data tell you. This is 2.18. Same, okay. And left tail and right tail, we can just, if you do the left tail, then will be just pt, right? And then you will be using this t, and then degree of freedom is n minus 1, okay? So this is the left tail, okay? This number, same as this number, okay? So this is how you do it from scratch, okay? So this is exactly this formula. You have two variables. You calculate the n. You construct a new variable which is difference. It's x1 minus x2. Okay. And then you calculate the mean of that. Okay. And you can calculate the t-stat. Okay. And then you can construct. Okay. That's how you are able to. No, it's okay. Just try to see. Any question? Okay. So that is constructing from scratch to let you know it's the same thing as you want to do, okay? But of course, this is much faster and this is something you should use, right? But trying to tell you that everything you see from the how you can do it from scratch, okay? So finally, I want to tell you this before we break. It's an F-test, okay? Using this data, we do the F-test, okay? F-test is rather easy, just call the var test. Okay. F test is called variance test. Okay. So if you don't know the syntax, it's very simple. Just go here, say question mark, called var test. Okay. Is F test. Okay. It just gives you X and Y and then less than more than. So very similar to this one. Okay. So let me copy from somewhere. Maybe copy with basic t test. Yeah, that's fine. Okay. This is the right thing we can copy. Okay. Okay. So with x1, x2, okay. We just do, we don't need this or this thing. Maybe we have this, okay. So this is var x1, x2, alternatively less. It's left tail, okay. Let's run this left tail, okay. And they would give you all the information, right? F, what is F? What is degree of freedom on the numerator, denominator? What's the p-value, okay? What is the hypothesis, okay? And the p will tell you that you would not reject at 5% or 10%. Also give you the confidence level, okay? Of course, you can also do the greater, okay? You can also do the two-sided, okay? So basically, okay, the same thing here, okay? Of course, the p-value is a bit different. Other thing are the same. And the interval, confidence interval are the same thing, okay? You can compare. Okay, so that's we end our first part with all the hypothesis testing using the R. Of course, in your free time, you can try to do the F test, okay, from scratch. Okay, so I will try to do it here. You show you the F test from scratch. Okay. So SD1. So you have break until 9:30. So I just try to show you. You can do the F test from scratch. Okay, so F will be just F will be just SD1 over SD2. Okay, and then we'll do the left tail test. No, will be just PF and then F. Okay, and then we have we define N already here, so the same number, so it's N minus. Maybe you just define it again in case you would be confused. N1 is the length of x1, N2 will be length of x2. Okay, N1 minus 1 and 2 minus 1. Okay, so this is the length. Okay, and you come look at the number here. Will be same as or less than the p value. Do I do it right? Let's see. Yes. Let me see the formula is it right? Yeah, S1s. Oh, not SD, sorry. Okay, this one is saying yes. Okay, so because I think I get it wrong. It says f is s1 square over s2 square. It's the f. Okay. So that's how you get this one. Okay, so it's just the variance, the sample variance of the first one, the second one, and the n, and then the ratio is the f, and then you calculate the left tail. Okay, the right tail also can do it, and both tail also. So this the free line is the how you calculate f test from scratch. Of course, the variance test is convenient. You can just do it without any problem. Okay, so let's break for 5 to 10 minutes. Then we will do the Anova. Okay, then we will talk about some regression. Okay, let's break. 好似呢個名唔係咁，我改個名啫。SX 所以叫翻個名。So let's start with Anova. Don't worry, Anova is very simple because we're not doing any calculation. I just tell you how to work on the Anova. Okay, so the answer is not that difficult. Okay, so Anova, basically remember the data we have at the beginning. Okay, Anova is this data, a bunch of X and bunch of its grouping. Okay, and grouping in the R, you can call it factor. Okay, so basically is you will be converting your data from a character data to a numeric data. That's how the R is doing. So you can see the numbers are 1, 2, 3. If you connect to group 1, group 2, group 3, you call a factor of this. You will see the R will tell you this is the factor. Okay, and because of factor, you can do Anova. Okay, it's not a number. It's a group 1, group 2, group 3. Okay, so here is much more common is the data you have is a bunch of characters, means A and B and C may be. You have NA, CC, UC, those kind of idea. Okay, it's a college. Okay, so you call it factor, that will be the data we have. Okay, so the first thing is probably you want to do a box plot. Okay, this is data. You have a factor. Okay, and remember you do data frame and do a box plot. So I will skip the box plot. But why you want to do this is because usually this is the first attempt. You see, looks like, okay, this group, the data is different from the other group, right? Because they based on the X and Y are the grouping, right? Looks like this group different from the others, right? So that's why you do Anova, you expect they have different mean. Okay, because group 1 is different from group 2, different from group 3. Okay, and we'll do Anova based on this. Okay, it's very simple. Just call Anova X and G, and then what data you're using, and then put a summary, then you're done. Okay, so that is how we are doing. Okay, so let's do Anova from scratch. We're doing one-way Anova. Okay, one-way Anova. Okay, so the data is, imagine we have some income of I don't know, bunch of income data, right? Maybe 10. This is the salary, 10K, 20K, 30K, 38K, 48K, I don't know, 25K. Okay, so just bunch of income data. Okay, and one-way Anova, so with different grouping. So grouping will be just, you have to tell me what is the what the grouping are there. So maybe we just have NA, UC, CC. How many we have? Maybe just NA and UC. Just make it easier. Okay, just maybe few groups is fine. And CC, and this is a NA, and this is another guy is a NA. Okay. And this is UC. I don't know how many we have. How many we have? Let's check. We have, let's run this and see how many we have. 7. Do we have the same number of grouping? 6. So say we need one more. We need one more CC, say. Okay. So we have 7 data here. Of course, actually we should one more. Okay. But this is the grouping and we generate randomly. Okay. This is the income. And this is the college we have. Okay. And so then, okay, this is a grouping. Okay. Let's clean this up. Too naughty. Okay. So we have 7 number of data here. Okay. And yes, you can see you have used the close bracket, right? To double quotation mark to tell this is the character. Okay. And because we really want to do Anova, so we just I think can we just do that? Let's try if we can just do that. Okay, let's try if we can just do Anova like this. Okay. We call data is called data.frame. Okay. And X and G. Okay. So this is, we create a spreadsheet. Remember what we do this. We have to create a spreadsheet here. Okay. So this is the data we have. Okay. This is exactly, we said at the beginning, there's a column of data. Column, this is usually the data you obtain from the web, right? Numbers and the description. Okay. So I think we can just do Anova in this way. So what we do is with a model, okay? Model, we just run Anova here, and formula is X based on the grouping, and the data is just data. Okay, okay, so able to run, hopefully, okay. And we just do the summary of the model. Okay, so basically, we go what we want. Okay, maybe just do model first because this just give a summary. So I think we can do an F test. The model itself, okay, give you everything there you need. Okay, this is sum of square, residual, degree of freedom. Okay, not really nice, but summary actually give you the Excel output, right? Degree of freedom, residual, right? So this is the mean, so DF, right? So this is sum of square within SSW. This is between group, so it's SSG. Okay, this is MSW, MSG. Okay, so this over this guy is the F value. Okay, this is the P value. Okay, the same as Excel. If you still remember Excel output. Okay, so we cannot reject this. Okay, so this is how you do a one-tail, one-way Anova. Okay, so there's one-way Anova. Now, let's do two-way Anova. Is there any question? I mean, just stop a little bit before we. I think just this is the 4 line is sufficient. Okay, this is how we do Anova. You can see it's very fast, much faster than Excel. You don't need to do the data analysis and the thing, just a several lines, just the data, tell them the model, and you're done. Okay, it's relatively easy. Okay. Is that fine? Okay. Then we will do a two-way ANOVA. That was also relatively easy. Okay. We have two-way ANOVA. Okay. So this is a group A grouping. Okay. And we also have group B grouping. Say, maybe this is the accounting. This is finance. Okay. And the other guy is finance. And finance again. And accounting. And accounting. And finance. Say. Okay, so this is data we have. Okay, so let's check with the, okay, they have all the 7 data, so that's fine. So we have A and B here. Okay, so that was data we have. Okay, so two-way ANOVA is not difficult. You just tell them, look at the slide, you tell them what you're going to do. Okay, what we're going to do is, remember the page in the slide we tell them is A and B and A intersect B and intersection. So the model is we have in our class is X is depend on the factor of A, factor of B, and also the interaction term. Okay, so we can just do this. We have A plus B and A intercept B. Okay, so we run this. Much faster than you can see, just then we're done, right? So just very fast. This is the something you want, right? Look at this is the SSA, SSB, SSAB, SSE, MSA, MSB, MSAB, and then MSE, right? And then this is just the F for A, F for B, F for C, right? And then look at the p-value. So none of them is significant from the other. So there's no evidence from this very rough data. You can tell NA or college, right, make a difference, right? Or the major make a difference, okay? Or the major college make a difference, okay? So that is the conclusion we have here, okay? No matter which kind of alpha you're using, you cannot, okay? So ANOVA is, you can see the power of R is much better than Excel, right? Excel, it takes some time to calculate. You don't need to, the data already give you in the nice form, you just put in, you don't need to handle the data, right? Remember, Excel data have to be, you have to put in the very nice form before you can do it. But this is the raw data, and raw data looks like this, right? Because the raw data, look at the raw data you have here, the raw data you have is not like this, okay? This is the data usually you got, right? The number, question number 1, how much you earn? Question number 2, which college you're in? Question number 3, what is your major? This is the data you have, right? If you try to collect a survey, you try to download data from the web, this is the standard thing you have, okay? So that's why the easiest thing to do is to use R, especially when you try to do ANOVA. Okay, regression may be similar, but ANOVA will be much convenient because Excel requires to put in this very special form. Okay, and here I don't even need to have an equal number of replicate, right? You can see in the question, right? I don't actually need to have the same number. Okay, of course, if we want, we need to be a little bit more careful in terms of putting this right, because I need to be careful if I want to you want to compare the same answer, right? Then you probably want to make sure that you have the same number of replica, but here just being for the ANOVA, for the R, you don't have to follow that. Okay, for Excel, you have to follow that one. Okay, is that okay? Is there any question for the R? If we're done, then we're done. Okay, so there's nothing else to teach for the R for the moment. Okay, we still have one more final class for R for the regression, but that would be also very easier as well. Okay. Any questions? So we are saying goodbye to our R for the moment. You basically know how to do R already. Okay. Of course, depends on what kind of how fast we go. If we still have time for the left before we exam, we will review something and then we'll continue to do some programming, because I think that would be more useful of our time, maybe, if you want to. Or okay, or maybe we can make it Q&A. It doesn't really matter. Okay, if there's no further question, then I will go to continue our journey on regression, because I think it would be good if you finish earlier, okay, rather than. So we still have half an hour, almost like, okay, 20 minutes, and I think I can go over the regression, and I show you how Excel you can do regression. Okay, so any question before I go on continue to do the regression? Okay, so don't worry, the regression will be very simple. We just finish the least square, and then we will tell you how to do it in Excel. Okay, so it's not going to be heavy. Okay, so regression, remember why we want to do regression. Regression, the basic idea is we have a scatter plot. Okay, so data X and Y. Okay, and the idea is I want to find the best line to fit this data. Okay, assuming they are related in a linear way. X and Y are in a linear way. Okay, so we want to have a line that will be best representing how X and Y are related. Okay, and what's the best here is what we call the vertical distance. Okay, just like this green dot, you compare to the line. Okay, the distance. Okay, and we want to minimize the square of this distance. So that's why it's called the least square method. Okay, is the vertical distance is being minimized. Okay, and this is what we want to do. Okay, and you may ask why we want to minimize the vertical distance, right? The main distance you can consider. You can also minimize the horizontal distance, right? You can also minimize the perpendicular distance. Okay, the main distance you can minimize. Okay, and in particular, the perpendicular distance is something you would use when you do the data science. Sometimes we call the Lyso regression, and then they actually, or ridge regression, they actually minimize the perpendicular distance. But for our purpose, we will minimize the vertical distance. The reason is being that we are in the classical environment where X is something we can control. Okay, you can imagine X is something we do experiment. We control X and see the effect of Y. Okay, so that's why X is we can control. So why we care about the vertical distance is the accuracy of the model, right? We want to X to tell me what's Y. Okay, that's why the distance is how accurate we are. Okay, so we want to minimize the departure from that line, and we care about the vertical departure, right? Because it's a model, we use X to help us to estimate or predict what's Y. Okay, tell us what the Y is, and we can control X. Okay, so that is the idea, and that's the idea behind what we call the least square method. Okay, the least square method is you have different data point there. Okay, just the green data point here. Okay, and I want to fit the line. Okay, and the line is what we call the line is called the Y hat. Okay, this is to distinguish the data is called Y. Okay, so that means that you go back to here. This okay is called YI hat here, and of course this is the y, the height is called yi. Okay, so you try to minimize the vertical distance of this. Okay, it's called the least square method. Okay, the vertical distance is yi minus y hat, as right here. Okay, it doesn't matter if yi hat minus yi or yi minus y hat. The reason is because we will take a square. Okay, the reason we take square same as the variance. Okay, variance is we take the square, and why we take square? Because we didn't show the proof here. When we do minimization, we will do the calculus, and for calculus it's easier to do a square thing rather than say cubic or absolute value. Okay, so if you learn calculus, you will understand why we do a square thing. Okay, and of course you may ask what happened if you do absolute value. Yes, there's something called the median regression, but we are not going to focus on that. It's the least square, it's just the square thing. Okay, so we just for each data point, okay, the n data point, every data point I take square the distance, I add them all up. Okay, I want to figure out what should be my intercept and my slope such that this sum is minimized. Okay, so in the other words, what I'm trying to do is just the verbal description of this is I want to find a line. Okay, it can be like this with the same slope, right? Maybe here the same beta, right? Or we have different alpha. Okay, so different intercept. Okay, I try to change the intercept or change the slope, okay, such that the vertical sum of the vertical distance squared will be minimized. Okay, in the other some ideas minimize a variance. Okay, in some sense, right? But variance is along this line. Okay, look at this line, go up and go down, right? And we want to minimize that. Okay, so in the other word, you look at the graph, it will be much easier. Okay, is this graph? Okay, is we try to look at this line above and down. There's a line there. We don't care about the red and blue. Okay, the distance we square it. Okay, add and all up. Okay, and this is a number. We want to find the smallest number. Okay, for every possible line. That will be our best fit line. This is called the least square line. Okay, and okay. And what is this least square line? Okay, turn out to be this formula. Okay, to get this formula requires some calculus, which we will not do. Okay, but we try to explain to you why this formula and what this formula means. Okay, the first thing is to notice. Okay, this slope intercept form. Okay, okay, this is the estimated intercept. This is estimated beta. Okay, so when you try to rewrite this formula, is y bar equal to alpha hat plus beta hat x bar, right? This is the slope. So this intercept, this is slope, right? And that means that if x bar is x value, the value of y will be the y bar, right? So that means that your line, the best fit line, will pass through the center of the data. Okay, let's do it graphically. Okay, let's see the graphically here. Okay, let's see the data. This is the scatter plot. This is x, this is y, and you can imagine there's a data here. Okay, this is data here. Okay, and look at the x, only look at x, mean of x will be here. Okay, just look, you forget about the value y, look at the every observation, the value of x, you can calculate the x bar, right? And this is just x1, x2, xn over n, right? And same, you have the y bar here, which is y1 up to yn divided by n. Okay, so this is the data. And what the least square, the best line you can imagine, will be a line that passes through the origin. Okay, there's no, but the center of data. So this is a point, okay, where the line must pass through. Okay, the next thing would be, we know this one point there. What we need is just the slope, right? So what should be the slope? Okay, what should be the slope? Okay, so we know we pass through this point. So next thing is what should be the slope? The slope is given by the following formula. Okay, let's go back to see it. Okay, looks complicated, but shouldn't be too worried about that. Okay, so this seems to be a rather complicated equation. Okay, but you can divide the denominator by n or n minus 1, depend on what you like. Okay, you divide n, the numerator will be covariance, the denominator will be variance. Okay, if you divide by n minus 1, will be the sample covariance and sample variance. Okay, you divide it, depends on what you like, doesn't really matter. Okay, so the beta, okay, the slope is just represented by this. Okay, so let's make sense of this. Okay, why the beta is related to covariance. Okay, remember what covariance means. Covariance is between two variables, is asking you how they're related. Okay, if it is 0, okay, they are not related at all. Okay, so then the slope will be, the covariance will be 0, the beta should be 0. Okay, look at the graph. Let's create another graph, okay, such that there, you know that what happened when the covariance is 0. Okay, the data look like this. The covariance is 0. Okay, because when x is above the mean, y can be above or below the mean equally, right? When y is above the mean and same, right? Because remember how we define covariance? Covariance, the interpretation is there is a x bar here, there's a y bar there. Okay, covariance said if x is above the mean, y should be also above the mean, or x below the mean, y should be below the mean. Look like this one is like equally scattered. Okay, above the mean up and down the same, below the mean also the same, above the y is also left and right is also very similar. Okay, so in that case, okay, it means that the best fit line is actually exactly this guy. Okay, in this case, alpha will be y bar here, beta hat is actually 0. Okay, because the best thing you can fit is like this. Okay, beta will be 0, and beta is 0, alpha hat will be y bar. Okay, because the best fit line is already just the horizontal line. Okay, the slope is 0. Okay, and if you have the data which is look like this, they look like this. Okay, and you immediately know the covariance is positive, right? Because when x is above the mean, y is above the mean, right? So the best fit line should be a positive line. And we know it's going to pass through the center, right? So this is the line, right? Actually, that's why it should be proportional to our covariance. Okay, so that's why the numerator is covariance. Okay, and the next thing is you ask is why your denominator is variance. Okay, that is just the scaling factor. Okay, of variance, because of, you can imagine that if my x, okay, and is multiplied by 10 times, okay, I shouldn't expect the formula is different, right? If I x, look at the variable, look at the case here, okay, look at the formula. Y is equal to alpha hat plus beta hat times x, okay? Suppose my x is go up by 10 times, okay? Means that suppose I use the data which is using the, I used to be use centimeter, okay? Now I use millimeter, okay? 10 times more, okay? So I should expect the graph, the everything calculation should be very similar to what we have seen, right? Of course, the alpha would change, right? But I shouldn't expect anything beta would change, okay? If your x multiplied by 10 times, okay, the numerator will be multiplied by 10, right? Just 10 times this, right? Because each data is 10 times more, and the mean also 10 times more, right? And denominator will be 10 times more, but the square is 100 times more, right? 10 times more, 100 times more is, this is 1/10 of time of original beta, okay? And that actually fit our equation because x is 10 times more, right? So that's the case, okay? So just cancel out, okay? And in that case, the intercept actually the same thing, right? Because imagine that the data you just multiply 10 times, okay? The intercept is where x is 0, okay? So the alpha should be unchanged. Okay, let me repeat the statement is if you multiply everything by 10 times or any times you want, okay, your intercept should remain the same, right? The intercept is where x is equal to 0, all right? So it shouldn't change it. So that's why when your data is rescaled, okay, you should divide the beta by the variance so that everything remain unchanged, okay? So of course, this is to explain why you have this. Of course, the real reason have to go to the math, go to the calculus, okay? So let us look at data here. We have 5 number, okay? So let's calculate the least square, okay? So one way to do, there's one typo here. One typo here, sorry. Okay, so you can calculate mean of x and mean of y. Okay, mean of x is 3, mean of y is 6. Just calculate, okay? And then you can subtract the mean, right? 1 minus 3 is -2, so on and so forth. And this is mean of y minus the mean of y, okay? And you can multiply these 2 columns, give you the product, right? -1 and so on and so forth. And this is the product of itself, right? This column square. And then sum of this column give you 7. Sum of each column is 10, okay? So that can calculate the beta, which is this over this. This gives you 0.7. And the intercept will be the mean of y minus the beta hat x bar. So 6 minus 0.73 is 3.9, okay? So for the remaining 4 minutes, let me do the Excel. Okay, we'll just tell you how to handle this guy. Okay, so let's have to open the Excel. So let me copy the data here. We have a y, with an x here. We have 4, 7, 6, 4, 9, and 1, 2, 3, 4, 5. Okay. So this is data. Okay. And remember, this is data we'll try to explain using the regression. Of course, you want to do a scatter plot first properly. Okay. And I hope you know how to do scatter plot, right? Just basically this one. Okay. This is scatter plot. Okay. Looks like there's some relationship there. Okay. So forget about scatter plot. Okay. Let's do the regression directly. Okay. Least square 1. So remember the formula to calculate beta, we need the covariance xy. Okay. We also need the variance y, the x, okay? And it doesn't matter we do the sample version or the population version, okay? So let's do this, okay? The covariance will be I just use the population version because that would be easier. That doesn't really matter anyway. Okay, so 1.4, and we do the variance p because we have using the variance. Okay, so this is the variance covariance. So that's why we know the slope or the beta, if you want beta. Okay, it's just covariance over variance. Okay, so it's 0.7. Okay, and to calculate the intercept alpha, we need to calculate the mean of x, so E of x. Okay, let's do EX. And you need the EY or x bar, y bar, maybe later. Doesn't matter. Yes, EX and EY, maybe. Okay. EX just be average of x. Okay. And mean of y just average of y. Okay. So I give you 3 minutes. Try to tell us what's alpha. Okay. If you're able to do it, you understand what we're doing today. If you don't know, then you may have some problem. So what we're trying to do is try to do the least square method. We are not in the regression yet, but it turned out to be these are the good estimator at the end, but find the alpha and the beta. We will skip the proof. If you want, you can ask me. I mean, it's not that difficult. Or just standard calculus. Just take the partial derivative and just solve it out. There's nothing. Just set it to 0, right? And just solve the system of equation. Take 咗個 D 完之後就係解咗個 equation 咪就係答案，冇特別嘅。Nothing special. Yeah, very well. I think some of you have did it. Okay, so I'll give you 1 more minute and you can try to tell me the alpha. How do you solve it? Okay, so alpha would be just look at the formula here. Regression. It's just mean of y minus beta times x bar. Okay, so basically just this guy minus beta times this guy. Okay, so y bar minus beta minus. Okay, so that is give us the beta and the alpha. Okay, so probably you will often say, oh, we commonly want to calculate alpha and beta. Can we have a shortcut? The answer is in this new version of Excel, we have this formula called slope and intercept. Okay, so we can just do that. We can have cost slope and intercept. There are two formulas that calculate directly. So this can be slope. Okay. Do note that you have to put in the y first before you put x. Okay. So because there's difference between x and y. Okay. Y here, x here. Okay. You will see this is the same thing as we have calculated. Okay. The slope is same as beta. Okay. And you can easily see we can also have the same thing intercept. Okay, so this is the same thing. So that's it for today. Today I released you 2 minutes earlier because oftentimes I take 1 or 2 minutes from you. So I just allow you 2 minutes to relax earlier. Okay, if you want to go, you can go. But I just answer question you want to have. But today what you learn is you learn all the R, how to do up to Anova, and we learn how to do regression. Okay, and next week we'll talk about probability model. So far the regression, we don't want to talk about probability, right? We will do hypothesis testing and estimation in the next class, and that's it for the whole semester. And then you can try to remember your homework on Sunday. Okay, I will see you next week. Okay, so I let you go 1 minute earlier now. If you want to go, you can go.